Hi students and friends, welcome to the channel Learn and Teach by Ayaz. This is your host and teacher Sayyid Ayazuddin Haider. I was doing past paper 9701, that is A levels chemistry, and I'm done with question number 1. So I will continue from question number 2. Here's question number 2. Water is an amphoteric compound that also acts as a good solvent of polar and ionic compounds. A. Equation 1 shows water acting as a Bronsted-Lowry acid. Equation 1, H2O plus NO2 minus reversible sign, HNO2 plus OH negative. Number 1, identify the two conjugate acid-base pairs in equation 1. In equation 1, if H2O is acid, so its base must be OH negative ion. So it's without H positive ion. So it must be conjugate base of acid 1. So acid 2, if I will select HNO2 as acid 2, so its conjugate base must be NO2 minus. Number 2, water also behaves as a Bronsted-Lowry acid when it dissolves CH3NH2. Explain the ability of CH3NH2 to act as a base. Here's CH3NH2. You know that NH, nitrogen carrying lone pair, it's in group 5. It's nitrogen, group 5, which means it has 5 valence electrons. 3 of the electrons are involved in the bonding, 1 with carbon, 2 with hydrogen. So lone pair is left. So that lone pair can accept a gain of proton or H positive ion. Lone pair on the nitrogen can accept or gain H positive or proton. Number 3, write an equation to show water acting as a base with CH3 COOH. So water is H2O. We have CH3 COOH. Water acting as a base, which means that the CH3 COOH, it's an acid. It must lose this hydrogen ion. And this will be taken by this H2O. So the product must be H3O positive plus CH3 COO negative. B, the ionic product of water Kw measures the extent to which water dissociates. H2O liquid gives H positive aqueous plus OH negative aqueous. Figure 2.1 shows how Kw varies with temperature. Kw is ionic product of water. This is a graph. On x-axis you have temperature, on y-axis you have Kw, which is in mole square per dm minus 6. Whatever the values are, they are multiplied by 10 raised to the power minus 12. Number 1, write an expression for Kw. For expression for Kw, it must be H positive, OH minus. Number 2, use information from figure 2.1 to deduce whether the dissociation of water is an exothermic or an endothermic process. Explain your answer. So you see, as it progresses with the rise in temperature, the Kw, it's rising, which means that Ka increases with temperature. So first of all, you write it's an endothermic. And equilibrium shift to the right hand side. Equilibrium shifts to right hand side. Or you can write K increases with temperature. Number 3, an aqueous solution has a pH 7 at 30 degrees centigrade. Use information from figure 2.1 to explain why this solution can be considered to be alkaline at 30 degrees centigrade. If you look at this Kw, it's increasing with temperature. This Kw, it's increasing with temperature at 30 degrees centigrade. Here it is. Concentration must be 1.5. Yes, 1.5 into 10 raised to power minus 14. Kw is increasing, which means it's alkaline. And it means OH negative ions are increasing. They are in higher concentration as compared to H positive. Therefore, it's alkaline. Kw increases with temperature, which means OH minus greater than concentration OH minus greater than H positive ion. Therefore, it's alkaline. Moving to next part. Number 3, the 3 physical states of H2O have different standard entropies as associated with them. Table 2.1 shows these S values. We have the values for solid state plus 48, liquid states plus 70.1, gas plus 188.7. Number 1, explain the difference in S values of H2O solid, H2O liquid. Definitely if you compare liquid to solid, there's more randomness. So you can say they have more disorder or randomness. H2O liquid particles or molecules have more disorder or randomness. Looking at the values, it's getting more positive. That's why randomness increasing. Number 2, explain why the increase in S is much greater when H2O boils than when it melts. You see, it's even greater, 188.7. So again, same logic. This time you write H2O gas particles or molecules have more disorder or randomness. That's why you see the value of entropy is higher in this case. Number 3, the energy changes for H2OS is H2OL are shown. Delta G 0, delta H plus 6.03. So we have delta G is 0 kilojoule per mole, delta H is plus 6.03 kilojoule per mole. Use these data to show that the melting point of H2O is 0 degree centigrade. First of all, we'll convert kilojoule into joule. So delta H is given. So we'll convert this into joule, which means you have to multiply it by 1000. So what we will get? We'll get 6030 joules per mole. Now we have the formula. Delta G is equal to delta H minus T delta S. So we need to calculate T here. So rearrange the equation. We will get minus T is equal to delta G minus delta H divided by delta S. Delta G is minus, delta H is 6030. What about delta S? We need to calculate delta S from solid to liquid. So liquid is the product and S is the solid. Product minus reactant. Entropy for the product minus entropy for the reactant. So we'll get 70.1 minus 48. minus 48. We get minus 6030 divided by 70.1 minus 48. 22.1. Six zero three zero divided by 22.1. Answer is 272.850. 272.850. It's minus. So we have the sign for T is also minus. So it will become T is equal to 272.850 or 273 Kelvin or 0 degrees centigrade. Hence it's proved. D. Metal air batteries are electrochemical cells that generate electrical energy from the reaction of metal anodes with air. The standard electrode potentials for the zinc air battery are shown. Here's the reaction. First one is of zinc hydroxide. Second one is of oxygen with water. Number one, calculate the standard cell potential, E cell of the zinc air battery. For air, here it's air, and this one is metal. It's more positive, so this becomes positive terminal, and that becomes negative terminal. So positive minus negative. Air has more potential to gain electron. So according to standard electrode potential values, according to standard electrode potential values, E cell must be equal to 0.4 minus 1.22 or is equal to 0.40 plus 1.22, which becomes 1.62 volt. 1.62 volt. This will be the final answer. Number two, the zinc air battery usually operates at pH 11 and 298 Kelvin. The overall cell potential is dependent on OH negative ion. The Nernst equation shows how the electrode potential at the cathode changes with OH negative ion. Here's the equation. Calculate the electrode potential E at pH 11. For this, we need the concentration of OH negative ion. First, you know that pH plus POH is equal to 14. pH is provided is 11. So 11 plus POH is equal to 14, or POH is equal to 14 minus 11 gives 3. Now we need to calculate the concentration of POH. POH, we know that POH is negative log of hydrogen ion concentration. Negative log of hydroxide ion hydroxide ions. So in order to calculate the concentration of OH negative, we need to take the antilog of -3. So antilog of -3. -3, calculate 0.001. 0.001 is the answer. 0.001. OH negative ion is 0.001. So the concentration of OH negative ions are 0.001. So putting the values in the Nernst equation, putting the values, we will get 0.40 minus 0.059. What about Z? It must be 2. Z must be 2. If you look at this, the number of electrons is 2. That's why I have to write 2 here for the electrons. So we have log OH negative ion is 0.001 whole square. Solving this, we will get plus 0.577 volt. This will be the final answer for this one. Moving to next question. Question number 3. Iron is a transition metal, group 8 of the periodic table. A1, explain why iron has variable oxidation state. So difference between 3s and 4d in case of iron, energy levels is very small. So that's why it loses electron from both the shells. That's why it's having variable oxidation states. Number 2, complete the shorthand electronic configuration of Fe and Fe3 plus. So AR is already provided. You know AR. Where is AR? Here is AR. It's 18. So AR means the configuration is already 1s2, 2s2, 2p6, 3s2, and 3p6. So they are done till here. So after this, for Fe, what you write? You write 3d6 and 4s2. Fe3 plus will lose 3 electrons, which means it will lose all the 2 electrons in the 4s shell, subshell, suborbital, and 1 electron from 3d. will be 3D5. B, an aqueous solution of FeNO3 whole thrice contains a complex FeH2O6 3 plus. When solutions of KSCN aqueous and FeH2O whole 6 3 plus aqueous are mixed, a color change is observed. The red complex FeH2O whole 5 SCN2 plus forms. Define complex. Complex is a molecule or ion formed by a central metal atom or ion is bonded by one or more ligands. A molecule or ion formed by a central metal atom or ion bonded by one or more ligands. Number 2, state the coordination number of Fe in FeH2O6 3 plus. It must be 6. 3, the HOH bond angle in water is 104.5, such as the HOH bond angle in FeH2O6 6 3 plus. Explain your answer. It must increase due to more repulsion. So the lone pair of oxygens used in the making of the bond. Bond angle is 106 to 108 because lone pair from O is used in making bond. Moving to next question. Number 4, explain why iron complexes are colored. That is due to splitting of degenerate d orbitals into 2 energy levels. And the reason is that electron moving to high energy state, they absorb energy or light in the visible region, and the colors observed other than absorbed colors. So you write splitting of degenerate. Degenerate means same energy level. Degenerate d orbitals into 2 energy levels. Electrons moves to a higher energy level. It's due to absorption of energy or light energy. Absorption of energy or light energy in the visible region and color is observed. We see colors, other than absorbed color. Number 5, aqueous solutions of complexes FeH2O whole 6 3 plus and FeH2O whole 5 SCN2 plus are different colors. Explain why these complexes are different colors. So delta E is different, or DD energy gap. Delta E or DD energy gap is different. Now, light absorbed or transmitted is of different wavelength. Light absorbed or transmitted is of different wavelength. Even you can write frequency or frequency. Moving to next question. See, table 3.1 gives values for the stability constant K stab of different complexes of iron. We have two different complexes, the stability constant given. Number one, FeH2O whole 5 H2PO4 2 plus can form when H3PO4 reacts with FeH2O whole 6 3 plus. Write an equation for this reaction. We have the reactants H3PO4 plus FeH2O whole 6 3 plus, and the product is FeH2O whole 5 H2PO4 bracket 2 plus. Now there must be a loss of water molecule as well as H positive ion from the H3PO4. So I will write H3O positive. This must be the other product. Number two, write an expression for K stability of FeH2O whole 5 SCN2 plus and give its units. So we have the product. This is the product FeH2O whole 5 SCN2 plus. So the reactant must be FeH2O whole 6 3 plus. It must be reacting with SCN minus. So the stability must be product by reactant. So you write Fe H2O whole 5 SCN2 plus divided by Fe H2O whole 6 and whole 3 plus multiplied by SCN minus. This must be K stability. What about the units? If you'll write the units for this one, we'll have mole per dm cube for the product. For the reactants, we have mole per dm cube. For other reactant, mole per dm cube. These will be cancelled out. So we will get dm cube per mole. Number three, use the stability constant data in table 3.1 to calculate the value of the equilibrium constant Kc for the following equilibrium. Kc must be, if you look at the data, we have these values and use these values. So this must be on top. Fe H2O whole 5 SCN bracket close 2 plus divided by Fe H2O 5 H2PO4 2 plus. Putting the values, what will we get? We'll get 1.3 multiplied by 10 to the power 2 or 130 divided by 5.9 multiplied by 1 or 59. So 130 divided by 59. 1 2.203. 2.203. 3 is the Kc for this reaction. Thanks for watching. Press like and share my videos. For more videos, subscribe to my channel, press the bell icon.